Human spacecraft have already reached every planet in our solar system. Rovers are moving across the surface of Mars at this very moment. A Probe plunged through the thick clouds of Saturn's moon system. Pluto, nothing more than a distant blur in our telescopes, has been photographed from less than 8 miles away. In a strange way, crossing billions of miles of empty space has started to feel almost normal. But there is one direction we have barely explored. One direction that sounds like it should be simple. One direction that feels like it should be easier than traveling all the way to the outer edge of the solar system. And yet, in reality, it is one of the hardest places to reach. Straight up, out of the flat plane where the planets travel, directly above the sun, or directly below it. The vertical escape route out of the solar system. At first, it seems almost absurd. Why not just point a rocket upward and go? Why not launch a spacecraft away from the planetary plane and send it above the sun's north pole or below its south pole? The answer is simple, but brutal. Physics does not allow it to be easy. What follows is the story of why escaping vertically from the solar system is harder than flying to Pluto. It is the story of what might be waiting above and below the sun if a spacecraft ever manages to get there. And it is also the story of one of the strangest maneuvers scientists are now seriously considering, a mission where a spacecraft must first fall toward the sun before it can ever climb away from. To understand why leaving the solar system vertically is so difficult, you first have to understand something invisible that you already have right now. Speed. You are moving at an enormous speed even while sitting still. Earth is orbiting the sun at roughly 30 kilometers per second, or about 67 miles per hour. That number is not an exaggeration. Every second, the planet beneath your feet moves about 30 kilometers sideways around the sun. And every spacecraft launched from Earth inherits that motion. When NASA, SpaceX, or any space agency sends a probe into space, that spacecraft does not begin from a true standstill. It already carries Earth's sideways orbital velocity. It is already moving around the sun at about 30 kilometers per second, just like the rest of us. Most of the time, this is a gift. If the mission is to go to Mars, that sideways speed does much of the work. The spacecraft is already moving around the sun in the right general plane. Engineers only need to adjust its path. Add a few kilometers per second of velocity in the correct direction, and the probe can be sent onto a trajectory toward another planet. That is why traveling through the planetary plane is relatively practical. The planets are all moving around the sun in roughly the same flat disk, and we are already part of that motion. But now imagine trying to go upward. Not toward Mars. Not toward Jupiter. Not toward Saturn or Pluto. Not anywhere else in the same planetary plane. Straight up, perpendicular to the entire system. Suddenly, the speed that helped you becomes the thing trapping you. To go directly upward, a spacecraft must first deal with the 30 kilometers per second of sideways velocity it already has. It cannot simply ignore that motion. If it launches up while still carrying Earth's orbital speed, it will continue moving sideways around the sun. It will not rise cleanly above the solar system. It will remain teed to the same basic orbital plane. So, to truly go straight up, the spacecraft has to cancel out much of that sideways motion first. Then, after fighting that enormous inherited velocity, it still needs additional velocity to climb out of the plane. The total energy required is staggering. Mission planners describe this kind of requirement with a term called delta V. Delta V means the change in velocity a spacecraft must produce using its own propulsion. It is one of the most important numbers in spaceflight because it tells engineers how much a spacecraft must be able to change its motion. Going from Earth orbit to Mars requires about 4 kilometers per second of delta V. But going straight up out of the ecliptic plane requires roughly 30 kilometers per second. Almost 10 times as much. That is the prison. Earth's orbital motion gives us free speed in one direction, but it also walls us in. We can travel around the sun fairly easily. We can send probes to planets that share the same broad orbital plane. We can hop from one part of the solar system's flat disk to another. But the moment we try to leave the plane itself, the problem changes completely. We are no longer using Earth's orbital motion. We are fighting against it. We are fighting billions of years of orbital momentum all at once. That is one of the most counterintuitive truths in astrodynamics. Reaching Pluto, a world billions of miles away, can require less energy than reaching a point only a few million miles directly above the Sun's North Pole. The destination may be closer in distance, but far harder in energy. Because vertical escape is so expensive, almost no spacecraft has ever truly made that journey. And because of that, nearly everything directly above and below the Sun remains a frontier even now. We have detailed maps of Mars. We have high-resolution images of Pluto. We have close-up photographs of comets, asteroids, Saturn's rings, and Jupiter's moons. We have sent machines across the solar system and looked at worlds that were once only dots of light. But the poles of our own Sun, the closest star to Earth, have barely been seen. That matters more than it might seem. The polar regions of the Sun are not empty or boring. They are connected to some of the most important and powerful solar processes in the entire solar system. The fastest solar winds come from the polar regions. The Sun's magnetic field reverses itself roughly every 1 year, and that reversal is tied to processes that begin near the poles. The entire space weather environment surrounding Earth and the other planets is shaped by what happens above and below the Sun's equator. And yet, for most of human history, we have observed the Sun almost entirely from the side. It is like trying to understand the weather of an entire planet while only ever standing at the equator. You might learn a lot, but your view would be incomplete. You would miss the polar systems. You would miss the full circulation. You would never truly understand the whole machine. Only 2 missions have ever managed anything close to a real polar view of the Sun. The first was Ulysses, launched in 1990 as a joint mission between NASA and the European Space Agency. To escape the ecliptic plane, Ulysses could not simply fly upward. It had to take a huge detour. The spacecraft first traveled outward to Jupiter. Then it used Jupiter's gravity like a cosmic slingshot. That encounter bent Ulysses' trajectory by nearly 80 degrees out of the planetary plane. From there, the spacecraft fell back inward toward the Sun on a highly tilted orbit. The mission worked. Ulysses gave scientists the first direct measurements of the fast solar wind flowing from the polar coronal holes. It revealed that the Sun's polar environment was different from the regions we normally observe from Earth. But there was a limitation. Ulysses was built with instruments from the 1980s. It did not carry modern cameras capable of directly imaging the solar poles. So, although it measured conditions there, it did not truly show us what the poles looked like. We learned about the polar regions, but we did not really see them. The second mission is happening in our own time. Solar Orbiter, a European Space Agency probe launched in 2020, has been gradually tilting its orbit using repeated gravity assists from Venus. Instead of using one dramatic Jupiter slingshot like Ulysses, Solar Orbiter slowly changes its angle over time. In March 2025, Solar Orbiter returned the first direct images of the Sun's South Pole ever taken in human history. Those images revealed a chaotic, magnetically tangled region, very different from the smoother solar surface we usually see from Earth. Think about how strange that is. Until very recently, no human and no robot had truly seen what the top or bottom of the Sun looked like from above. Not really. Not directly. The closest and brightest object in our cosmic neighborhood, the star that makes life on Earth possible, still has 2 regions that we have only just begun to photograph. Ectris, the shape of our bubble. There is another reason vertical escape matters. We do not actually know what our own solar system looks like from the outside. Around the Sun is an enormous bubble called the heliosphere. This is the region where the solar wind dominates space. The Sun constantly releases streams of charged particles outward, and those particles push against the interstellar medium beyond the solar system. Inside this bubble are the planets, the comets, the asteroids, and every human spacecraft we have ever launched. Outside, it is the deeper galactic environment, a region filled with cosmic rays, interstellar particles, and material from the space between stars. The heliosphere acts like a protective boundary, shielding the solar system from some of that environment. For decades, scientists imagined the heliosphere as something shaped like a comet. The standard picture showed a rounded front, where the solar system pushed into the interstellar wind as it moved through the galaxy, and a long trailing tail behind it. It seemed reasonable based on the data available at the time. It became the textbook image of our solar system's outer bubble. But in 2020, a team led by Meraf Offer at Boston University used a new model based on NASA data and came to a very different conclusion. The heliosphere might not be comet-shaped at all. Instead, the model suggested that it could look more like a deflated croissant, a curved central bulge with two shorter jets curling away from it, and no long tail like the old textbook version. The problem is that we still do not know for certain. Why? Because we have never seen the heliosphere from outside, and we have never sent a probe far above the ecliptic plane to observe it from a useful angle. The Voyager spacecraft did cross the heliopause, the boundary where the solar wind gives way to interstellar space. That was one of the greatest achievements in space exploration. But Voyager crossed that boundary sideways, more or less in the same plane as the planets. That data is extremely valuable, but it is also limited. To truly understand the shape of our home in the galaxy, we would need a spacecraft traveling far out of the ecliptic plane, looking down at the structure from above. NASA has a mission called EMAP, the Interstellar Mapping and Acceleration Probe, designed to improve our understanding of this boundary from inside the heliosphere. But for a direct view of the bubble's true shape, there is only one real solution. Escape vertically. Get above the planetary plane. Look back. That vantage point has never been reached by any spacecraft. And without it, we are still living inside a structure whose true shape we do not fully know. Act 4. To climb, you must first fall. So how can engineers solve the vertical escape problem? The obvious answer would be to build a bigger rocket. But that does not really solve it. The energy required to cancel Earth's sideways orbital motion is simply too large for any practical full load. A spacecraft cannot just brute force its way upward with conventional propulsion. So scientists have considered a much stranger solution. It is called the Solar Oberth Maneuver. This idea has been discussed in mission design circles for years, and it is slowly moving from theory towards serious mission concepts. The maneuver works almost backward from the way most people imagine spaceflight. If you want to climb above the sun, you do not immediately aim upward. You do the opposite. You drop toward the sun. The spacecraft falls inward, pulled by solar gravity, gaining speed as it descends deeper into the sun's gravitational well. By the time it reaches its closest approach, called perihelion, it may be traveling at hundreds of kilometers per second, possibly more than 100 kilometers per second. And then, at that exact moment, it fires its engines. That timing is the key. The principle comes from Hermann Oberth, who described the idea in 1929. A rocket burn is much more effective when performed at high velocity deep inside a gravitational well. The same amount of fuel can produce a much larger increase in orbital energy if the burn happens when the spacecraft is moving extremely fast near the sun. In empty space, that fuel would give a certain amount of energy. Near the sun at immense speed it gives far more. It is not a normal gravity assist, because the spacecraft is not stealing momentum from a planet. But in effect, it produces a kind of slingshot-like result. The sun's gravity accelerates the spacecraft first, and the engine burn at perihelion converts that situation into a huge gain in energy. The fuel carried from Earth becomes far more powerful than it would be almost anywhere else. After that burn, the spacecraft can be moving fast enough and in the right direction to finally climb out of the ecliptic plane. It could head toward the solar poles. or it could even escape outward from the solar system on a high-inclination path. In this mission architecture, the dive becomes the launch pad. To go up, the spacecraft must first fall down. Solar sails are another possible part of the solution. Mission concepts, such as the proposed solar polar imager and the more recent high-inclination solar mission, use enormous reflective sails. These sails do not rely on fuel. Instead, they use the pressure of sunlight itself. Photons from the sun carry momentum. When they strike a large reflective sail, they push it. The force is tiny, but continuous. Over time, that steady pressure can slowly change a spacecraft's orbit. A solar sail could gradually tilt a spacecraft's path out of the ecliptic plane. The process could take years, but it has one huge advantage. It does not require propellant. The longer sunlight pushes on the sail, the more the spacecraft's inclination can grow. Scientists have also considered combining both ideas. A spacecraft could use a solar sail to spiral closer and closer to the sun. Then, at its closest approach, it could perform an over-Earth maneuver to redirect itself vertically. After that, it could continue using the sail to travel into the polar regions. This kind of architecture may be one of the best ways to finally give humanity a clean view of what lies directly above and below our star. Act 5. What we would see from above. So if we ever succeed, what would a spacecraft actually see from directly above the sun? First, the view would physically change. The ecliptic plane is not empty. It is dusty. Earth, like every other planet, moves through a thin haze of dust left behind by billions of years of comets, asteroid collisions, and the slow grinding of material throughout the solar system. You can actually see this dust from Earth under the right conditions. On a very dark night, just after sunset or shortly before sunrise, a faint triangular glow can appear above the horizon. This glow is called the zodiacal light. It is sunlight reflecting off dust particles inside the plane of the solar system. It is the inner solar system lighting itself up. A spacecraft rising above the ecliptic would climb out of that dust within months. Once above the plane, the view would become much cleaner. There would be less scattered light, less background haze, less interference from the dusty disk we live inside. That kind of vantage point could be incredibly valuable for astronomy. A telescope placed above the ecliptic might detect faint signals that are almost impossible to see from within the dusty plane. It could become one of the best locations for instruments searching for signs of life around other stars. It could help study exoplanets, weak infrared signals, and distant objects normally drowned out by the glow of dust. From that same vantage point, another instrument could study the cosmic microwave background or examine the structure of the Milky Way's galactic plane from a cleaner position. Second, the solar environment itself would change. Near the sun's equator, the solar wind is slower and more turbulent, moving at roughly 400 kilometers per second. But above the polar coronal holes, the spacecraft would enter a different kind of solar wind. There, the flow is faster, steadier, and thinner. Fast solar wind from the polar regions can travel between 700 and 800 kilometers per second. A spacecraft moving through that stream would experience a radiation and plasma environment very different from what probes usually encounter near the ecliptic. That matters for science, but also for engineering. The polar solar wind could affect the lifetime of spacecraft electronics, the design of shielding, and the type of instruments that could survive and operate there. At the same time, it would provide valuable measurements of a region that shapes space weather throughout the solar system. Third, there's the bigger picture. From far above the ecliptic plane, the solar system would finally appear as the disk it truly is. The spacecraft would see the planets moving in a flat ring around the sun. It would see dust concentrated along the plane. It could observe the heliosphere wrapped around the entire system, revealing whatever shape it truly has, whether it resembles a comet, a croissant, or something even stranger. For the first time, we would be looking down at our own cosmic neighborhood the way astronauts look down at Earth from orbit. And that is the astonishing part. We have never seen that view. Not once. No human and no robot has ever sent back a photograph looking down on the solar system from outside its planetary plane. Of all the images humanity has captured, the surface of Mars, the storms of Jupiter, the rings of Saturn, the heart of Pluto, distant galaxies, nebulae, and black holes, one of the most important images is still missing. A picture of our own solar system from above. A view of the place we live, not from inside the disk, but from outside it. And that leaves one final question. If you had to design the first mission to climb directly above the sun, which path would you choose? Would you choose the slow, patient method, a solar sail gradually pushed by sunlight over many years? Or would you choose the violent, dramatic method, an overdrive that sends a spacecraft falling toward the sun before firing its engines at the perfect moment and climbing away? Tell us in the comments. And if you want to know what actually waits in those unexplored regions above and below the disk of our planets, watch what exists above and below our solar system. Next, this video explains the journey. That one shows the destination.